In this video lesson, we're going to cover example 3, which is the third example and final example of any of the energy equations that we've covered. Let's go ahead and read this situation. A 55-kilogram man bungee jumps from a 60-meter high cliff with his 20-meter bungee cord. As he nears the bottom of the cliff, his cord stretches to its maximum displacement, allowing him to fall 8 meters from the ground. What is the spring constant of the bungee cord? Draw bar charts before you solve. Okay, so this one's a little bit more complex because we really have to imagine what's going on in this scenario. So like always, let's go ahead and draw some pictures before we solve anything with our bar charts or with our calculations. So we have a man that's standing at the very top of a cliff that is 60 meters high. At that point, the man is obviously not moving. He is in the air, and he's attached to a bungee cord that is not stretched or compressed, but instead is at equilibrium. Then the man jumps off the cliff and is allowed to go down to where the man reaches maximum displacement of the bungee cord, that is 8 meters above the ground. It is these two scenarios or situations that we're going to draw our bar charts for, and then hopefully use that information to figure out what the spring constant is for the bungee cord. So let's think initially, what is the energy or energies that are there at the top of the cliff? He's at the top of the cliff, and we're assuming that the ground at the bottom is our reference point. So we definitely have EG. The man is not moving yet, so there's no EK. And since the bungee cord is not being stretched or compressed at the top, there is no elastic energy either. So the total mechanical energy is going to be residing all in gravitational at the very beginning. Then in bar chart number 2, this is going to be where he is at the point right here where the bungee cord has reached its maximum stretch or maximum displacement, and he's 8 meters above the ground. Since he hasn't hit the ground yet, which thankfully, because that would be an awful bungee jump trip, he's still above the ground, and so we still have a little bit of EG. Now think about it. When you reach your maximum stretch on a bungee cord, that's going to be where your kinetic energy is zero, because you're not moving at that point. So there's actually no kinetic energy at this point when he's stretched the bungee cord its maximum displacement. Since the bungee cord is actually stretched, there must be some elastic energy there. And so in the second bar chart, we're actually going to have EG and E elastic. I'm going to guess that EG is probably lower than E elastic since he's 8 meters above the ground. So I may draw 1 square for EG and 6 squares for E elastic. Now that we have our bar charts, let's go ahead and start calculating. Let's start out by calculating, if we can, what the total mechanical energy is in the tire system. I'm going to try to get that from the first bar chart since there's only one energy there of EG. If I can find out what my EG is in the first bar chart, that will be my total mechanical energy. EG is found by taking mass times G times H, and I do actually have all three of those values. The man is 55 kilograms, acceleration of gravity is 10 meters per second squared, and he's at the top of a 60-meter high cliff. So the gravitational energy and also the total mechanical energy is 55 times 10 times 60, or in other words, 33,000 joules. Now, in situation number 2, that energy needs to be split between EG and E elastic. I can solve for EG because I'm told that he is 8 meters above the ground at that point. So MGH, I'm going to do this one in red. MGH for when he's at the very maximum stretch is going to be his mass of 55 kilograms times acceleration of gravity, 10 meters per second squared, and then times 8 meters. When I multiply all three of those together, I end up getting that the EG at this point is 4,400 joules. So that means the elastic must be the difference between the total mechanical energy and the gravitational potential energy. So I'm going to take 33,000, which is the total, minus the 4,400, which is the gravity, to get my elastic energy is 28,600 joules. I'm going to use this energy in order to figure out what my spring constant is. Elastic energy is 1/2 kx squared. So I'm going to set that 1/2. K is what I'm solving for. And then I get to this point where it is time to put in X. Now, X is going to be the amount that the bungee cord stretches. Let's look back at the problem. What do we know about the bungee cord? We're told that the bungee cord is 20 meters long when it's unstretched. That means the bungee cord would get to only right about here off of a 60-meter high cliff before it has to start stretching. So at the point right here, this is 40 meters above the ground. How much more does the person go before he stops? We're told he goes to 8 meters. So if the bungee cord is unstretched during this part, and it's only during this part that it stretches, we can take the difference between 40 and 8 to figure out how much it stretches. And so 40 minus 8 gives us that the bungee cord stretches an additional 32 meters before it stops the man. So 32 meters is going to be my X, and don't forget to square that. Okay, so now I'm going to set that equal to 28,600. So 28,600 joules is equal to 1/2 K, and then let's do 32 squared right now. 32 squared gives me 1,024. And if I solve for K, let me extend the page here. If I solve for K, give me some more space. There we go. I'm going to do 28,600 divided by 1/2 and divided by 1,024. That gives me my spring constant of 55.86 newtons per meter. This concludes the video lesson on example number 3.